Hi, this is Hung Zin from Nanyang Technological University. In this video, I will introduce our work, Mitigating Neural Network Overconfidence with Logit Normalization. This is a joint work under the supervision of Professor Bowen and Professor Yuxuan Li. Firstly, we start with a simple case to introduce what OOD detection is. Here, we trained a classifier with a training set to recognize cat or dog. However, when we deploy our trained model to the online service, there might be many inputs from unknown distributions, like a panda or bear. We call such inputs as out-of-distribution data or OOD data. Formally, we use standard supervised learning setting in the training time. During the test time, we consider the case that test data might come from a different distribution, whose label set has no intersection with that of training distribution. Our goal is to detect OOD inputs in the test time, and these inputs should not be predicted by the model. Generally, we formulate OOD detection as a level set estimation with a scoring function. We choose a proper threshold so that a high fraction of in-distribution data is correctly classified. Before our method, we first consider a question: why model trained with cross-entropy loss tends to give overconfident predictions. To understand the underlying reason, we decompose the logit into two parts, magnitude and direction. Through the two propositions, we find that increasing the magnitude will cause a higher confidence score, but don't change the final prediction. It means that the optimization on the training loss would increase the magnitude for a smaller loss. To provide a straightforward view, here we show the dynamics of logit magnitude during training. Indeed, the cross-entropy loss encourages the model to produce a larger logit magnitude for both in-distribution and OOD examples. The large norms directly translate into overconfident softmax scores, leading to difficulty in OOD detection. To alleviate this issue, our key idea is to decouple the influence of logit's magnitude from network optimization. We expect to keep the logit magnitude a constant during the training. In this work, we employ Logit normalization. In particular, the logit vector is normalized to be a unit vector with a constant magnitude. The softmax cross-entropy loss is then applied on the normalized logit vector instead of the original output. Interestingly, our loss function can be viewed as having an input-dependent temperature. By Logit normalization, minimizing the logit norm loss can only be achieved by adjusting the direction of the logit output. Then, the resulting model tends to give conservative predictions, especially for OOD inputs. We explicitly show the advantage of the logit norm loss in this figure. For the cross-entropy loss, the softmax confidence scores are extremely high for both the in-distribution and out-of-distribution examples. Differently, our logit norm loss produces almost uniform softmax probabilities for OOD input. In this figure, we can see that if we train with cross-entropy loss, the softmax scores for both in-distribution and OOD data concentrate on high values. For the logit norm loss, the network produces highly distinguishable scores between ID and OOD data. We also analyze the softmax output by visualization. From this figure, we can see that when we train with logit normalization, the softmax outputs provide more meaningful information to differentiate in and out distribution samples. In the experiments, we compare the OOD detection performance on models trained with cross-entropy loss and logit norm loss respectively. We can observe that our method drastically improves the OOD detection performance by employing logit norm loss. In this table, we also empirically show that logit normalization can consistently improve existing scoring functions, such as MSP, OOD, energy, and grad norm. On the other hand, we show that logit normalization can maintain comparable classification accuracy on in-distribution examples and enables better calibration by way of post-hoc temperature scaling. We have shown the strong performance of our logit normalization on OOD detection. One may have a question: can we achieve a similar effect by imposing a penalty on the logit magnitude? Here, we show that explicitly constraining logit norm via a regularization penalty cannot help the OOD detection task. Specifically, the gap of logit magnitude between in-distribution and OOD examples is smaller than that of logit norm. In summary, we introduce logit norm, a simple fix to the cross-entropy loss by decoupling the influence of logit's norm from the optimization. We show that logit norm can improve both OOD detection and confidence calibration while maintaining accuracy on in-distribution data. Finally, we contrast with alternative methods like logit penalty and demonstrate the advantages of logit norm. Thank you for your listening.